You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait, what's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars. So this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our sun. This giant structure is called the South Pole Wall. It's located about 500 million light years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light years away. Rockets can cover that distance in about 73,000 years. So the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light years long. To give you an idea of how large that is, the Milky Way is only 100,000 light years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light years across. So, it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew! This is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. But these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the two universes connected for a while. It's like 2 drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the 2 bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through inter-universal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you managed to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
This is our home planet Earth and its satellite, the Moon. Zooming out, and here's our solar system. A bit more, the Milky Way galaxy. And we're a small dot among an infinite number of stars. Now, even farther out, a cluster of galaxies. Dots and swirls in the endless space. Further, there's Laniakea supercluster. That little dot here is our galaxy. Moving on, Hydra Centaurus supercluster. Huge clusters comprising thousands of galaxies are no more than a speck from here. Next, Pavo Indus supercluster. This is an area 200 million light-years wide. We can zoom out until we see the entire observable universe. Each little dot in here actually contains thousands of galaxies and quadrillion stars. Scientists speculate that our universe may look like a bubble, and that bubble might collide with another universe. Yes, other universes could exist. Actually, even a whole infinite number of those. All of them could have appeared after the Big Bang. The collision between them isn't impossible either. At least, it might have happened before. And the proof is here, in the direction of the constellation Uranus. This place is called Uranus supervoid. It's about 1 billion light-years wide. By comparison, the width of our entire galaxy is only about 100,000 light-years. There's absolutely nothing in this place, and it may be a trace from an old collision between our universe and another. Scientists think they were passing by each other. When the distance between them was minimal, the gravitational forces of the bubbles began to pull toward each other, just like two drops of water trying to connect when they're close. But the speed of the universes was too high for them to continue interacting. So the other universe just tore out a piece of our bubble. There might have been about 10,000 galaxies in that void, and all of them were either destroyed or taken over by the other universe. Let's travel to the edge of our universe to see how this collision might have taken place. We're 10 billion light-years away from our home. Here, in another galaxy, we see amazing nebulae of different colors and shapes. And if you look in the other direction, there's a huge wall moving at us. All these bright sparks on it are enormous galaxies about to collide with us. But in fact, it's a humongous mirror that only reflects our universe. Here, space-time is distorted and begins to be pulled into another universe at a tremendous speed. The usual law of physics may simply stop working at this point. Gravity may disappear, and with it, all the stars would explode, and people on the surface of planets would hang in weightlessness. But if the universes didn't go at a tangent but crashed directly into each other, things would be much scarier. The enormous amount of collision energy would probably cause an incredible explosion. Its force would simply destroy everything in our bubbles. Still, the two bubbles might begin to merge too. At first, all galaxies at the edge of the universes would be torn apart, but then the merger would begin. The galaxies would start moving chaotically. They would fly past each other, break apart, collide, and explode. The collision of two galaxies is an accident of enormous proportions, and it might happen to our home quite soon, in space terms. The Andromeda Galaxy is heading our way. It's a spiral galaxy about twice the size of ours, and there are about 1 trillion stars there, which is twice more than in our Milky Way. At the very center of this bright galaxy lurks a dark beast, a black hole. Its weight is 2 and 8 zeros of the Sun's mass. Red giants hundreds of times larger than our Sun. Pulsars emitting enormous amount of energy like spotlights. Rogue stars, and many large and small black holes. This soup of dangerous objects is moving toward us at 68 miles per second. A trip to New York to Los Angeles at that speed would only take half a minute. The disk of Andromeda can already be seen with the unaided eye on moonless nights. As time goes on, it'll get even bigger. As Andromeda gets closer to us, its gravitational force will begin to stretch the arms of our spiral galaxy. It'll begin to unwind. The stars and planets will lose their orbits. One possible scenario is that an unknown asteroid, or even a dwarf planet from the Andromeda Galaxy, will crash into the Earth at an incredible speed. Our planet will explode just like a balloon from this impact. Oh, goody. Another option involves stellar collisions. Our Sun would face another star. The bigger star will slowly begin to consume the smaller one. First, it will steal the light upper layers from it, and then it will eat it just like spaghetti. Or even like rigatoni. When a large star reaches its critical weight, it will burst. This explosion will destroy everything around it, including our solar system. Perhaps the shockwave will even reach other neighboring stars. Yet another scenario is that our solar system will be thrown into dark space. Imagine a tennis ball tied to a rope. You take the rope and spin the ball over your head like a sling. Then you let go of the rope and send the ball flying. This is what will happen to the Sun and all the planets around it. We'll find ourselves in dark and cold space. But life on Earth will not be affected. We'll still have our bright star to keep us warm. The only disadvantage is that all the stars in our night sky will disappear. And the most likely possibility is that the merger of two giant galaxies will have no effect on us at all. The thing is, the distance between stars and planets in space is enormous, so they can all just mix together and form one giant cloud. It would be like shoveling fine sand through a big sieve. The objects won't interact with each other. But the most interesting thing will happen to the black holes in the centers of our galaxies. Right now, there's a dense cluster of stardust and stars around them. As Andromeda and the Milky Way come closer together, they will begin to dance with each other. Gee, will it be the twist or the foxtrot? And when the black holes get close together, they'll begin to swallow all matter around one another. Billions of tons of colored stardust, asteroids, and star particles will fly toward the very center of either black hole. It might seem like this process happens very slowly, but it's an illusion. Super heavy objects like black holes warp the space-time grid, so time is much slower near black holes. And all objects that seemingly stay on the event horizon for weeks or even months are actually long gone. When the black holes finally come together, they merge into one supergiant black hole, but its mass is slightly less than the combined mass of the two dark monsters. Some of their weight is transformed into collision energy. This energy is released so strongly that its waves can be felt in other galaxies. Now, a huge black hole gathers all this dense and hot core of the two galaxies around itself. At some point, the black hole feels full and throws out powerful jets of energy into space. This is called an active galactic nucleus. It's one of the brightest phenomena in the universe and the most powerful source of electromagnetic radiation ever known. These jets may be more than 5,000 light-years long. By comparison, the distance from Earth to the nearest star, Proxima Centauri, is only 4.2 light-years. And the explosion that accompanies the jets has the power of 100 supernova explosions. Wow, blows my mind. The blast wave from this event could even reach the edges of a new galaxy, and this outburst would be visible from millions of light-years away. Now, there are dense clouds of multicolored dust at the center of merged galaxies. The weight of these clouds is so great that they begin to shrink and take on a round shape. Gradually, they become so heavy that they compress the core and nuclear reactions start inside them. The temperature begins to rise and soon, boom, there's a supernova. It's a veritable fireworks show at the center of the galaxies. Stars erupt from the fog and form new hot worlds. At this point, the arms of the two galaxies that were previously pulled out slowly return to their former shape. The super-heavy center of our galaxy has such a gravitational force that it affects stars and nebula hundreds of thousands of light-years away. The galaxy's arms twist again, and we see the new and finished galaxy, the Milkomeda, or Milkdromeda. Hey, how about the Milky Way? Blah blah blah. Well, that's hard to say. So check this out. Astronomers have discovered an exoplanet they're calling Super Saturn. It's got rings over an AU wide. An AU is the astronomical unit, the distance between the Sun to the Earth. That's an incredibly huge ring system, hence its name. Super Saturn is being called Mamajek's object after the astronomer who led the team to whom we owe the discovery. Professor Eric Mamajek of Rochester University in New York found Super Saturn while scouring through data downloaded from wide-angle transit observations. WASP is the acronym for Wide Angle Search for Exoplanets. It's an ingenious project developed in the year 2000 by astronomers at Queen's University in Belfast, Northern Ireland, and St Andrews University in Scotland. Using 4 telescopes, the CCD video cameras on the scopes record the slight dimming of starlight caused by objects passing in front of stars. This is called the transit method of exoplanet detection. So, for example, the planet Venus transits across our view of the Sun every couple hundred years. A black dot, the silhouette of Venus, is visible, crossing in front of the Sun as Venus passes between our line of sight and the Sun. This tiny eclipse causes the amount of sunlight coming to Earth to be reduced by a minuscule amount, also known as teeny tiny. The same is true for all the stars in the Milky Way that have planets going around them. Exoplanetary transits in front of stars must be in direct line of sight with Earth for the starlight to be dim. Such transits do not occur very often. That's why thousands of stars must be looked at simultaneously for as long of a duration as possible, between 4 and 8 hours a night. WASP was created to stare continuously at as wide of a range of stars as possible. Maybe one of them would show an exoplanet transit. That translates into a lot of data being produced, about 40 gigabytes per viewing session. Computer scientists at Leicester University in England developed a computer program to store the data and generate photometric graphs of the light intensity of each star. Open University, also in England, joined the WASP project, took this data, and made it available for research by astronomers worldwide. The graphs of the intensity of starlight show that changes in its brightness are called light curves. These graphs have two axes. One is in the timeline axis, the other one is the intensity of light. As the object, considered an exoplanet, though it could also be a brown dwarf star, crosses in front of the star, the timeline axis keeps track of how swiftly it is moving. It tells us how close the object is to the star, while the brightness axis keeps track of how much the starlight dims. This way, we can find out how large the object is. Now, obviously, big objects will dim the light more and be easier to detect. At present, Earth-based equipment is not sensitive enough to measure the dimming caused by planets as small as Earth. Neptune's size and larger ones are the limit for WASP. However, the James Webb Space Telescope, which is now in operation, has a much greater sensitivity and will be able to resolve the transits of Earth-sized exoplanets. Now, I know you want me to get to Super Saturn, but there's something else you should be familiar with before we get there. If the exoplanet has an atmosphere, or, in the case of Super Saturn, a ring system, the starlight from the star the planet is transiting will shine through the atmosphere or ring system, and that can be detected too. The light curve will show less dimming in the photometric data, because not all the starlight is being blocked. Some light is still getting through the atmosphere or rings. This is important because it gives astronomers a reading of the atmosphere. The James Webb Space Telescope is fitted with spectroscopes that can determine the gas content of the transiting exoplanet atmospheres: oxygen, methane, carbon, etc. The WASP project has been really catching on. There's a Super WASP project now consisting of WASP North and a WASP South. One looks at the sky above the northern hemisphere, the other looks at the sky above the southern hemisphere. There's also a Next Generation Transit Survey, NGTS, based on the WASP project. It's automated, so astronomers don't have to stay up all night sipping coffee, but they can if they want to. Located at the European Southern Observatory in the Atacama Desert in Chile, the NGTS scans millions of stars and has discovered over 100 exoplanets down to a size as small as 3 times the size of Earth. NGTS has started a Planet Hunters Club on social media. Citizen scientists can search the online database of light curves and perhaps discover your very own exoplanet. What had been a strictly British effort started by 1 or 2 astronomers is now a worldwide phenomenon. With the ability to read the spectroscopic signatures of atmospheric gases during exoplanet transits, a new idea emerged: technosignatures. That is, specifically identifying gases in exoplanet atmospheres that are produced by civilizations. The James Webb Space Telescope can do this. Gases from pollution, such as chlorofluorocarbons (CFCs), can be seen spectroscopically if present. Tritium from fusion reactions, if they have them, can also be detected, along with heat patterns from cities on the planet's surfaces. Technosignatures is a recent concept that originated after the WASP project started. Who knows what it will turn up? Now, let's get back to Super Saturn. The star that Super Saturn orbits is J1407, a small, dim, sun-like pre-main sequence star of the 13th magnitude. Huh? Well, the human eye can only see stars to about the 6th magnitude, and each magnitude is 2.5 times dimmer than the previous one. So, it's not an exceptional star, just another telescopic star out there in the Scorpius Centaur region of the night sky. J1407 is a young star that hasn't yet settled into its stable, long-duration phase. This is important because Super Saturn, officially J1407b, is showing signs of having a ring system in an early stage of development. Super Saturn's light curve was tucked away in the mountain of data from the SuperWASP project. Professor Eric Mamajek and his associate Matthew Kenworthy of Leicester University studied the data thoroughly and produced a detailed report on it. Knowledge depends on good data. The horizontal axis of J1407b's light curve, the time axis, is what's causing all the hubbub. It took Super Saturn weeks to transit across in front of its parent star, 56 days to be exact. Planetary ring systems that we are familiar with in our solar system orbit right around the equators of the gas giant planets and are very thin, from only a few meters thick down to a few centimeters. In a telescope, Saturn's rings will seem to disappear when the planet is at zero inclination toward Earth. Saturn must be inclined at an angle in relation to Earth to see Saturn's beautiful ring system. It's something everyone should make a point of seeing: Saturn in a telescope. If Super Saturn's rings block most of the light from J1407 for 56 days, it means that the planet had to be orbiting at a steep inclination to its star. If it were at zero inclination, we wouldn't see the rings blocking any light. Therefore, the orbital time could be determined, 10 years minimum to 200 years if the orbit is highly elliptical. The superplanet itself is calculated to be 24 times the mass of Jupiter, which means that if it is gaseous, it could be a brown dwarf star. Super Saturn appears to have a Mars-sized object orbiting around it, because there is a huge gap in the rings that was most probably cleared out by a large object. The Cassini division in the rings of Saturn is where the moon Mimas has cleared out a path through Saturn's rings. The light curve of Super Saturn has only been observed once. All the exoplanet detection systems are keeping an eye out for it to come back around J1407. No one knows when that will occur. Some astronomers have suggested that J1407b is a brown dwarf star system in itself, merely passing in front of, but not connected to, star J1407. An orbital reappearance of Super Saturn would disprove that conjecture. The center region of Super Saturn blocked out all the light from its primary star. This is what indicates that the ring system is new and in an early developmental phase. Over time, the very dense ring mass close to the planet is expected to thin as all this matter gets absorbed into the planet or ejected into space. This is what has happened with our solar system's gas giant planets. The Mamajek object is a shocker. Never before or since has a light curve been detected like Super Saturn's. Super Saturn has added a new chapter to our understanding of the formation of ring systems. So, here's to you, Super Saturn. Hope to see you again soon.